All right, so section 8.2 is operations with matrices. We want to look at, in section 8.1, we looked at kind of defining a matrix and writing it as an augmented matrix or a coefficient matrix or a row matrix or a column matrix, and how we could work with it with a system and elementary row operations, Gaussian elimination, all of that good stuff. Today we want to look at adding, subtracting, scalar multiplying, and matrix multiplying. Talk a little bit about some of the identities, and then we'll be using those things in the upcoming lessons as well to help us do some other applications. So the first thing they tell me on page 567 deals with the equality of matrices. And they tell me that two matrices are equal if they have the same order and all of the same elements. Now, the converse of that then would also be true. If they tell me that two matrices are equal, then I can assume that all of their elements have to be the same. So like this first example that we've got here, where they don't tell me what x and y are and they ask me to solve for those, well, because they tell me these two matrices are equal, then I know that the same elements, or that the elements are all the same. So this is 2 and this is 2. This is 5 and this is 5. This is 3 and this is 3, so that means x equals 3. This is 8 and this is 8, so that means 3y minus 1 is equal to 8, and then I could solve that to figure out that y is 3. So that's one way that I can use the equality of matrices to help us. The next thing they tell me is that matrices can only be added or subtracted if they have the exact same order. It has to be a 1 by 4 and a 1 by 4, a 2 by 3 and a 2 by 3. They have to have the exact same order if you're going to add them or subtract them, either one. If they don't have the same order, like if they ask me to add a 1 by 2 and a 3 by 5, I can't do that. So I just say impossible, can't be done, undefined, something along those lines. So example number 3, they give me matrix A, which is a 3 by 3, and matrix B, which is a 3 by 3. Now, those are square matrices. They don't have to be square matrices in order for me to add them or subtract them. That just so happens to be the example that they gave me. So if I want to add matrix A plus matrix B, I'm going to take what's in the first row, first column, plus what's in the first row, first column, and I'm going to put that answer in the first row, first column. Same idea with the next one. I'm going to take first row, second column, plus first row, second column, and put that first row, second column. And then we keep going with that same idea. 4 plus 0 is equal to 4. Negative 3 plus 1 is equal to negative 2. And we keep going all the way through the matrix that way. Now, you do not need to show this step for me. The only reason I put that in there is that if you were looking back at this later on, you would have some work to see where we came up with the answer. But I absolutely understand if you have no work at all for a problem like this and you go straight to your answer, that's fine. The next thing they show me is scalar multiplication. Now we need to distinguish today between scalar multiplication and matrix multiplication. Scalar multiplication is when you multiply something by like a scale of 2 or a scale of 1/2. That's like doubling it or halving it. You usually think of scale when you make like a scale drawing of something that's really large and you scale it down, or something really small, you scale it up. That's the same idea of what they're talking about here, just multiplying it by a factor of something. In this case, we're multiplying by a scale of 3, so we are tripling every single one of these values. So we're going to go through and say 3 times each of these values. So 3 times 2 is equal to 6. 3 times 2 is equal to 6. 3 times 4 is equal to 12. 3 times negative 3 is equal to negative 9. You get the idea. We would go the rest of the way through the matrix doing that same thing. Okay. And again, no need to show this work here. I just wanted you to have something to refer to as to where we got those answers. If I want to subtract two matrices, I'm going to do it the exact same way that I did addition. Let's say that this had been A minus B right here. Then I would have said 2 minus 2 is 0. 2 minus 0 is 2. 4 minus 0 is 4. I can even put these things in combination where I can do addition or subtraction or scalar multiplication all at the same time. And that's what they have me do in the last part down here. They asked me to do 3a minus b. So I could go ahead and do my scalar multiplication of 3a. As a matter of fact, we've already done that right here. So this is the matrix 3a. So I can take 3A and then I can subtract matrix B. So I'm just going to go what's in the first row, first column, minus what's in the first row, first column, and that answer goes in the first row, first column. What's in the first row, second column, minus what's in the first row, second column, and that answer, bless you, goes in the first row, second column. And we would keep going that same way. Now, sometimes they'll ask me to solve an equation that deals with matrices. If I'm solving an equation with the matrices in it, I would recommend to you, let's say that we're right back with those same matrices that we had in example 3. I'm going to make a huge mess of my equation if I replace A with a 3 by 3 and I replace B with a 3 by 3. And then I've got to turn around to get X by itself. I've got to subtract A to the other side. So now I've got to turn around and subtract that 3 by 3 over. It's a whole lot easier if we just leave those letters in place. We're going to use capital letters for our matrices. We're usually going to write them in a set of brackets or braces like you've seen them doing. So I can leave my capital letters in there and solve with it in its letter form, and then when I finish, then I can go back and put my matrices in. So if I were to subtract A from both sides and then multiply both sides by 1/3, I would have that X is equal to 1/3 of matrix B minus A. That's very similar to what we just did a second ago where we did scalar multiplication and subtraction. I know how to do that already. So it's just a little easier to work with in that form. On page 570, they give me some properties of matrices. These are properties for matrix addition and scalar multiplication. We're going to have some properties of matrix multiplication in a second. But properties of matrix addition and scalar multiplication. First, they tell me that the commutative property of matrix addition works. A plus B equals B plus A. So that's helpful if in a problem they give me two matrices and maybe for number 1 they ask me to find A plus B and number 2 they ask me to find B plus A. It's the exact same thing. I save myself the effort if I know that property. The second one they give me there is the associative property of matrix addition, which basically says if you have 3 matrices that you're adding, you can add them in any order. You can add A and B first, or you can add B and C first, or you can add A and C first. We'll get the same answer. The third one is the associative property of scalar multiplication. So it shows you that if you're multiplying a matrix by 2 different scalars, you could multiply the scalars first and then multiply by the matrix. That'd probably be fastest. Or you could multiply one scalar by the matrix and then multiply the other scalar by the matrix. So again, you can alter your order of multiplication. Number 4, they give you the scalar identity. If you take 1 and multiply it by any matrix, you're just going to get that matrix. So that's the identity. Then they also show you the distributive property there in 2 different ways. They show you the distributing one scalar and distributing a matrix when you have 2 scalars. Okay, so all of those properties hold true, and they can save us a little bit of time and energy. Over on the top of 571, they give me a couple of bold print terms. They give me the zero matrix. A zero matrix is just a matrix made up of all zeros. If you take a matrix of all zeros and you add it to another matrix that has the same order, what would you get? That same matrix, right, what you started with. So for that reason, the zero matrix is also your additive identity matrix. So 2 different names for the same thing there. The zero matrix is also the additive identity matrix. It is the identity for addition with matrices, because if you add it to a matrix with the same order, you'll get what you started from. All right. If there is anything confusing about operations with matrices, it's matrix multiplication, because it does not work the way that we think it should. Here's what we think it should do. 2 times 7 is equal to 14. That's not a 14. 3 times 1 is equal to 3. Okay, this apparently is not going to work the way I think it should. Matrix multiplication does not work like matrix addition or matrix subtraction. And so that's what's confusing about it. So let's look at some rules for matrix multiplication. When you multiply your matrices, the inside numbers in your order must be the same if you're going to multiply. The outside numbers in your order tell you the order of your answer. Right? Here's what they're talking about. With addition and subtraction, the order has to be exactly the same in order for you to not get an undefined. That's not true in multiplication. You do not have to have the same order. If you'll notice down here, I'm multiplying a 1 by 2 and a 2 by 3 with no problem at all. They don't have to have the same order. What they do have to have is the inside numbers in the order have to be the same. So like this is a 2 by 2 and this is a 2 by 2. The inside numbers are the same. They're both 2. Down here, this is a 1 by 2 and this is a 2 by 3. The inside numbers in the order are both 2. They're the same. But down here, this is a 3 by 2 and this is a 1 by 3. The inside numbers are not the same. So if the inside numbers are not the same, it can't be done. Impossible, undefined, can't be done, something along those lines. The outside numbers in the order are also significant because, as they mentioned here, the outside numbers tell me the order of my answer. So I look at this one and I know, okay, my answer is going to be a 2 by 2. I'm going to come over here and I am literally going to draw out for myself with these little red blanks. I'm going to draw out a 2 by 2. So I'm going to give myself 2 rows with 2 columns. I'm going to give myself 4 little blanks over there. I have to know what I'm trying to get to because my answer tells me how to multiply. So for instance, if I'm trying to find the answer that goes in the first row, first column, I'm going to multiply the first row in the first matrix by the first column in the second matrix. If I'm trying to figure out what goes in first row, first column, I'm going to multiply first row by first column. So I'm going to do 2 times 7 and 3 times 8. And then I'm going to add those two values. So 2 times 7 plus 3 times 8 is where we get that 38. Look at another one. If I want to know what goes in the first row, second column, I'm going to take first row times second column. So I'm going to do 2 times 1 and 3 times 6. 2 times 1 plus 3 times 6 is where I get that 20. Second row, first column, I'm going to take second row, 5, 4, times first column, 7, 8. So 5 times 7, 4 times 8. And then second row, second column, I'm going to take the second row times the second column. So 5 times 1 and 4 times 6. Look at another one. For this guy, we've already talked about the fact that the inside numbers are the same, so I can multiply even though my order is not the same. The outside number tell me what my answer is going to look like. The outside numbers are 1 and 3, so that tells me my answer is going to be a 1 by 3. So I'm going to come over here before I ever start, and I'm going to draw for myself a 1 by 3. I'm going to give myself one row with 3 columns in it, so I'm going to draw those 3 red answer blanks. So I start off and say, okay, if I need to know what goes in the first row, first column, then I'm going to take the first row, 6, 8, times the first column, 1, 4. So that would be 6 times 1 and 8 times 4, and then I'm going to add those together. To figure out what goes in the first row, second column, I'm going to do first row times second column. So 6 times 5 and 8 times 6. And then to figure out what goes in the first row, third column, I'm going to do first row times third column. So 6 times 3 and 8 times 2. Okay. So the inside number tells me whether I can multiply or not. The outside number tells me the order of my answer. That is pivotal because if I don't know what I'm trying to get to from my answer, then I don't know what I'm supposed to multiply to do it. Okay. All right, then over on, and we already mentioned this guy down here, since the inside numbers were not the same, then it could not be done, so we said undefined. All right, then they give me some properties of matrix multiplication on page 574. And at first glance, it doesn't really look like a big deal. It's a lot of the same properties we had for addition a second ago. I've got the associative property of matrix multiplication, 2 different distributive properties, associative property of scalar multiplication. What is really significant is not as much what is there on the page, but what is not there on the page. What is not there on the page is the commutative property of matrix multiplication. The commutative property says that A times B is equal to B times A. Like, 2 times 3 is equal to 3 times 2. That is typically true, but with matrices, it is not. A times B is not the same thing as B times A. Here's a really great example of that. Come back to this guy right here that we were just working with, right? We had a 1 by 2 times a 2 by 3. So maybe this is matrix A and this is matrix B, all right? If I tried to reverse the order, if I tried to say matrix B times matrix A, so I put this one first and this one second, all I did was reverse the order. That would be a 2 by 3 times a 1 by 2, right? If I have a 2 by 3 and a 1 by 2, the inside numbers are not the same. Not only am I not going to get the same answer, I'm not going to get an answer at all. That's impossible. It can't be done. It's undefined. So that's an easy way for us to see that A times B not the same thing as B times A with matrices. All right, there on 574, they also give me the identity matrix of multiplication. We've had the identity of addition. Remember that the 0 matrix was the identity for addition. The identity for multiplication would be what matrix can I multiply by my matrix and still end up with the matrix that I started with, my matrix that I started with. And the identity matrix is a matrix that has all ones in its main diagonal and zeros everywhere else. It can be a 2 by 2, a 3 by 3, a 4 by 4, a 5 by 5, a 20 by 20. It depends on what you're working with. But the identity matrix is going to have all ones in its main diagonal and zeros everywhere else. Okay? So we're going to be using that identity and this idea that AB is not the same thing as BA and some of that to help us solve some equations in the next couple of sections. All right, so here's our homework for tonight. Notice that we are going back and doing a problem from section 8.1. That's extra practice with that, putting something in row echelon form that we were working on last night. Again, we are still not using a calculator to do these. I know that we could do all of these on the calculator. We will once we do all of them by hand. Then we'll learn how to do them all on the calculator. And of course, we've got our quiz tomorrow over 8.1 and 8.2. No graphing calculator for that either. You can use a scientific if you want something just to help you add, subtract, multiply, divide.